Okay. So, setting up your notes, just on a sheet of paper, you'll need to, probably want to go ahead and put the topic on there. And if any of you guys are done like average strategies, essential questions, something that you should be able to answer by the end time, class is over. And then of course the date, would be important too. You don't need to write it down like this stuff right here. Those are just instructions. So wouldn't really need to put those in your notes. And then the blue and the purple and the green parts here, we will go over like kind of more individually. So I wouldn't write those down right now. I'm just kind of giving you an idea of what we're going to do. Normally, like the last couple of years when I've done this activity, I've just had the students do all this on their own while I was kind of doing some, beginning of the year stuff, like going around talking to people, getting things set up and things like that. So normally this has been more of an independent or like small group activity, but with the distance stuff, I wanted to go through this with you guys. So just kind of a start to working together. So again, we will individually go through each of these things, and I wouldn't write down the blue, purple, or green stuff. Just kind of get your notes set up so you're comfortable. And then later on, I'll just kind of show you what I'm expecting on the worksheet, and I talk to you about how you're going to turn that in and stuff like that. So. Does anybody need me to wait any longer so I can get the topic or essential question written down?
I do, please.
Okay. Just let me know when you're ready. My hands are really cold. So, you're right.
What page in the packet should we write these on?
On the packet. This will just go on a piece of paper.
Oh, okay. All right.
You're going to do some work in the packet today. There are a couple of like notes sheets in the packet, but yeah, not this.
All right.
Am I good to go, or do you guys want me to wait a little bit longer? All right. Okay. So yeah, we're just gonna be doing some definitions here today. So, and then I'll do a couple sketches with you, but I think it should be pretty rough. Apologize ahead of time for any handwriting issues. If you can't read anything or anything like that, if I'm moving too fast, I definitely have a habit of like talking really fast so that my words kind of mush together. So let me know if I got to repeat anything or handwriting is atrocious or anything like that. Please let me know. So domain is the set of all possible inputs for a function. So the set of all possible inputs for a function. Like I said, normally I would have students look up all this stuff on their own, and then we'd come back together and say, hey, Addie, what'd you get for yours? Aiden, what'd you get for yours? And like kind of compare definitions and see if there's like pieces of ones that, need to be like put together, or if there was something like that was completely missing from everybody's, and I'd had to kind of like fill that in. So, okay, I see, Mason. Mason, we're just working on a piece of just paper right now, taking some notes. So if you want to leave some space at the top, I can flip back and you can see like the topic and heading and stuff like that for the notes, but we just started. So, so what usually I end up, or one of the things that's just kind of like textbook definition, you might want to add that it's the, all the x's or all the x values. So when we say inputs we were talking about x values. And then range is kind of the inverse of that. So that'd be the set of all the outputs. Or all the possible outputs. So if we're talking about inputs, that means x's, right? So we're talking about outputs. That would lead us to talking about y values. So. Does anybody need more time there? Thanks, Andre. Okay. This we're going to define discrete functions and continuous functions. We're just going to do a quick graph of those. Always worried about defining these quite right, so I want to make sure I look at the definition just more. All right, so a discrete function. So that's a function where the domain and range are sets of particular numbers. And usually like integers or whole numbers. Not very happy with my handwriting there. And when I draw it, it'll make maybe a little clearer what I'm talking about here. So I'm just going to do a real quick sketch. So I'm just going to draw a quick set of axes. Of course, I have our y-axis and our x-axis. So what you're going to see when you look at a discrete function or you go to draw a discrete function is that it's just points. And it doesn't have to be like in any particular pattern or anything like that, but it's just points. And so that may be something you want to add on to that. That would be an example of a discrete function, the graph of a discrete function or a discrete relation. And then a continuous function. I'll talk more about like kind of the context of these two things once I describe what a continuous function is. It's a little easier once you can talk about both of them. So that's a function where the domain and the range are all numbers in an interval. And what we would see with graphing a continuous function. So we may start off with points, kind of like we did with the discrete, but with the continuous function, all of the points between the points also have value. And so they get connected. So continuous is definitely one of the words that a lot of students get confused by, in Algebra 2 and college algebra. We have kind of a different definition of it in our lives, what continuous might mean. And so when we think about it, trying to apply it to math, we get confused with that. And so a lot of times when we think about what's something that's continuous in life that might go on forever and keep going, really what continuous means in math is that the points are connected. Okay. And so that all of the points between the points that maybe we have data for also have value. So we can connect to those points. So the points are connected. So if you're asked to draw a discrete graph, you should just be drawing individual points. If you're asked to draw a continuous graph, you can plot the individual points and then draw the curve or the line that goes through them. Okay. This is definitely something we're going to be talking about quite a bit in this unit. So kind of like foundational vocabulary. So why do we have these two things? Why would we have a discrete graph or discrete values versus why would we have continuous values or discrete or continuous graph? So if you think about a lot of stuff that goes on nowadays, is data driven, right? Think about, you're going online and then, Facebook's collecting your data and Google's collecting your data. And you think about businesses, it's they're collecting data all the time to figure out what their customers are up to. And, when you sign up for those purchase cards, or the discount cards, at Dillon's or something like that, they're doing that, giving you those discounts because by collecting your data, they're actually, figuring out more about you and then able to hone stuff towards you and, basically get you to buy more stuff. Sports, so much data collected about sports, statistics is such a big deal with sports. So data, we're collecting all this data. So what if your job was to collect data for a company that sells hats, right? And so you say, okay, they open their store, they open a new store in Lawrence, and you say, okay, the first day you sold 23 hats at your store. The next day you sold 12 hats at the store. And the third day you sold 35 hats at the store. Right? And you're just collecting data and you're getting all these little data points. Right? And so you would start, plotting those data points on a graph or using other things to manipulate that data to try to figure things out. Well, with something like hats or people or objects, things that we count, we can't say, well, one day you sold, 10 hats and the next day you sold 20 hats. So on day 1.5, you sold 17.5 hats. That doesn't make sense in that context. We can't sell so many percentage decimals of hats or fractions of hats. Okay. Or if I was trying to count how many people were going on a ride at amusement park or how many people were using the bus every day, I couldn't use decimals of people. And in that context also day 1.2 doesn't make sense because we would be looking at the number of people on each particular day. They'd be separated. So those points would have no value between them because the numbers between the points don't make sense. So we can't have fractions of those things that we're talking about. Whereas if I was looking at the temperature and at 7 o'clock tonight, it's 60 degrees, and then at 10 o'clock tonight, it's 52 degrees, that we'd be able to understand that, okay, these numbers along the way represent real things okay, this must be about where 7:30 was, and okay, it's 59.2 degrees, and oh, this might be where 825 is, and that's okay. That's like 53.7 degrees. Like those things make sense to us when they're things that we can measure, like time, temperature, volume, weight, things like that. Things we measure. The decimals make sense in those contexts, and we can see how things would change along, like between places where we might have particular sets of data, right? Because we're not just going to take data all the time because we can't store all that information, but we will take a data point here, take another data point here, and say, oh, between them, we can kind of see how things change. We can make sense of that. Okay, so there's certain times when we can take information and we can only use it for what we have, right? It has to be discrete data, discrete information. Whereas other times we can take an information and then connect the dots and say, oh, we can think about this continuously. Okay, so that's why we have two different types of graphs, right? And so it's just something we'd be thinking about, is whether that information should be just points. Do decimals make sense in context, or not make sense? Sorry, or can we connect the points? Decimals do make sense in context. Fractions make sense in context. Yeah, so it's all very contextual. Right? We got to figure out from what's going on if it's okay or not. Right? Is there anything about discrete or continuous that seems fuzzy right now? Thanks, Audrey. Thanks, Kyla. Okay. Anybody need more time there? Thanks, Ed. Thanks, thank you guys. Appreciate the feedback. All right. So last little group of stuff we need to talk about. We're going to define what a function is as a thing, and then we're going to talk about 4 different types of parent functions. So each of these types of equations is its own particular type of parent function. So, okay. So in general, what is a parent function? This is something we're going to talk about a lot throughout the year, like parent functions and just different type of functions. Of course, math class shouldn't be too surprising, but so a parent function in general is the simplest equation or function in a family of functions. So I might be using a couple words in context that you're not used to, like parent and family. Like wouldn't really necessarily think of those as being math terms. Essentially, if you think about like a family of functions that you guys have spent time studying already, would be linear functions. Most of Algebra 1 is dedicated to helping you guys understand linear functions. Now you spent a lot of time talking about slope and how things change and like y-intercept and standard form of a linear equation and point slope and things like that. Spent a lot of time solving linear equations. Like if I said, hey, solve 10 equals 3x plus 2 or something like that, like that's something you should be able to solve. And then towards the end of that year, you started talking about the family of functions or equations known as quadratic equations, where we started throwing like x squared at you, like x squared plus 3x minus 7. Like, hey, let's graph that, or like, oh, let's solve that. Like, that's a different family of functions. And quadratic functions are like the main focus of Algebra 2. And then we'll work on cubics and exponentials and a couple other ones later too. So just kind of, you guys have talked about these things, like you just probably never called them families maybe. So, but that's not really a big deal. But the parent is the simplest function in that family. So if we think about the family of linear functions or family of linear equations, the parent, so being the simplest, is y equals x. Or a different way to write that would be f of x equals x. So this is the linear, or the parent function for linear functions. is y equals x or f of x equals x. And what that would look like, so I'm just going to draw a real quick graph. Listed axes, I got my y-axis, got my x-axis. The simplest line we can draw would go from the top right to the bottom left through the origin. That would be the graph of the equation y equals x. You know, things you guys spent time talking about in Algebra 1, like, okay, well, what if I asked you guys to graph y equals 1/2 x plus 2? Like, you know, that's something you should kind of have tumbling around in there. I know it's been a while. You know, but like, what did slope do? Like, if I change the slope of the line, what does it do to the graph? You know, if I change this y-intercept, what does it do to the graph? Okay. So this is a more complex equation, but it's still in the same family because it's just a plain old x. Okay, so these two functions are in the same family, but this is the simplest one, so it's the parent, and then this would be a more complex, so you could kind of think of it as the child, but you don't use that term really. Okay. Then the next one would be quadratic functions. So the parent there is y equals x squared, or f of x equals x squared. Yeah, I'm just going to do a quick little sketch. So a quadratic function comes out as a parabola, which is a U-shaped graph, and it should hit the origin and then curve back up. It's not very good. Try that again. You know, the line went through the origin. This parabola has its what's the vertex at the origin there. I don't know if you guys can see me drawing those dots there or not. And that's y equals x squared. So that's the simplest parabola we can draw. Another family is the cubic. And so the parent is y equals x cubed, or f of x equals x cubed. This one's a little trickier. It's going to start in the top right and then curve towards the origin and then curve away and then head pretty quickly down. It's not too bad. It's like a really stretched out S. Again, it runs through the origin. But that one grows really quickly because they're taking those x values and we're cubing them. Now it's like 1 cubed is 1, but then 2 cubed is 8. You know, and then 3 cubed is 27, 4 cubed is 64. Those numbers grow really fast. Like we're seeing really steep curve here. In the same way down, like, you know, -1 cubed is -1, and -1 or -2 cubed is -8. So it drops rapidly. And then the last one is the exponential. Also a very fast moving graph. You know, if you think about exponential change, or if you talked about exponential growth and exponential decay in your biology class, what you're referring to there is very fast change. The parent for exponential functions is y equals 2 to the x. So notice how the variable's up there in the exponent spot now, rather than, like here we had x to the third power, x to the second power. Here now it's a number to the x power. Or f of x equals 2 to the x. And what that looks like. So what we're going to see there, so on the left-hand side, if you think about like what's going on there, if we say like what's 2 to like the -5 power, we end up with a really, really tiny decimal, and 2 to the, oh, what was that? Sorry, Audrey, I didn't see your text or your chat till just now. So if we have negative numbers in the exponent spot here, it gives us very small decimal values. It doesn't give us negative values like this did. So we're gonna have very, very small numbers here. Basically what you're gonna see here is along the x-axis, it's basically just gonna kind of be flat as far as what our eyes can see. And then we're gonna move through the point 0, 1, and then it's gonna shoot up really fast. So what I'm gonna sketch, again, just try to run flat along your x-axis, but just above it. And as you get close to the y-axis, you're gonna start curving up. You're gonna pass through the point 0, 1. And then you're gonna shoot up real fast. So on that left-hand side, what you don't want is you don't want it to touch the x-axis. You definitely don't want it to like cross through the x-axis. Okay, so it should be just above it. There is actually like a slight incline here, but our eyes just can't see it because the numbers are so small. We can't really perceive it. So, and then as soon as you cross that y-axis, it shoots up really fast. So that's an exponential function. Audrey, is there anything you want me to go back over that I was moving too fast through for you? Or anybody? Okay, thanks, Sam. Thanks, Phil. Does anybody need me to stay on my iPad, or I can show you what I'm expecting on the homework assignment type thing? That's just how it goes, isn't it, Audrey? I'll stop sharing this, and I'll share my PDF and show you kind of what I'm expecting on the homework. Oops. Yes, I can. All right. So when you're doing the homework, so there's 6 problems, so it's gonna be like the first page and then the second page. And it's kind of weird how it printed on the back of the cover. So the first thing you're gonna do is identify the domain and the range, right? And so domain is all your inputs or your x values. So you're gonna list out all your x values, and then the range would be all the outputs or the y values. So you're gonna list out all your y values. And I've already had some students make some mistake on this today, multiple students. So please pay attention here. Every graph you're going to do today is going to be a discrete graph. So that means I'm expecting to see only points on your graph. Do not connect them with a curve or line. Okay. So you'll go ahead and plot your points. Kind of double check yourself on there. It's been a while since some of you guys have done that. seen some students plotting things wrong. It happens. Just kind of watch yourself. So domain, fill out the domain, fill out the range, and then you're going to say what type of equation is it. And so what I mean by that is which of the parent functions does it look like, right? So if you're seeing, if all your points line up, in a line, then you'd say, oh, that's a linear equation. If they make a U shape, then you say, okay, that's my quadratic equation. If it's that S curve, then okay, that's my cubic equation. If it seems to be kind of flat on one side and then start to shoot up, then okay, that's my exponential. Okay, so this third line should be words. I've seen some students writing numbers in there, not what I want. Okay, and the last one is now you're going to try to figure out what the equation is. Okay, and then this is definitely something that we're just asking you to try. We're not expecting perfection here by any means. I want you to think about, and I'm going to show you, I'm going to flip you back to my iPad real quick to talk to you about kind of what you should be thinking about to do this. Since it has been a little while, I'm just going to give you a little bit of a prompt. But when we want you to write the equation, kind of how should you be thinking about that? Okay. So let's say that your graph looked like this. Let's say that's hitting there at 2. Okay. So what type of function are we looking at? Linear, right? Yep. Okay. So what's the parent function for linear, right? That's y equals x. And y equals x looked like that. So our equation that we're about to write better look something like y equals x. Except for there's something different about our graph, right? It doesn't pass through the origin. It's passing through 2. Well, how do we write the equation that looks like this, but passes through 2 instead of the origin? So how do we change this to make it pass through 2? How do we, guys, any ideas on how we do that? What we would write? How would we change this equation so that it passes through 2 instead of 0? Or that it slides 2 up? Okay, right on. Y equals x plus 2. Okay. So I kept the parent function because we were able to identify it as linear, but I was like, oh, if I push it up 2, then, right, to kind of represent what's actually happening here, right? You guys all should remember some stuff about slope. You should see some of that in the worksheet, like that the slope will be different. I haven't really been talking about that yet, but I kind of want to see what you guys know. Another idea, just to help you a little bit again, is if your points were doing something like this, let's say this is down here at -3. Kick this off to the side there. So what type of function is this? Quadratic, okay. And so then we think, okay, well, what's my parent function for quadratics? What should this function look like if I go to try to, well, the parent function was this, right? Where that lowest point hit there at the at 0, 0, and that was just y equals x squared. Right? So our function needs to be related to that. It needs to have an x squared in it, but we need to be able to change it by shifting it down 3. Right? So how would we write the equation differently to shift it down 3? Yeah, x squared minus 3. So some of the things you guys are going to see, it's not everything by any means. There's a couple other things that, again, the slope stuff I didn't mention, but I brought it up that you will see some issues with slope. I know one of the quadratics looks different than this in a particular way. I want to see if you guys can figure out how that would change the equation. But again, really just trying to see what you guys got, what's going on up in your gray matter. So the domain stuff kind of expect you to get, the range stuff kind of expect you to get, be able to identify the type of the equation. I expect you guys to get. Writing the equations is more like you should be feeling that out right now. So, but it's definitely something we're going to be working towards during this class, so that I can give you a graph and you should be able to write its equation. So, not expecting to get that right now, but I just want you to give it a try. And we'll kind of see what you know, see what you think, and work on helping you from there. So, sure, yeah, I can do that, Audrey. But the rest of the time is you're to be working on your worksheet. You have 6 problems to do, okay? And then you need to either scan that or take a picture of that and submit that to the Google class. And I've already